Notice, and this is the typical copyright. This is an overview of how the videos from this section will be published, totally or partially on YouTube. Note this one here. It says here, partially published. Change of plan. Upon completing this objective and this video, 715, and taking into account its difficulty, I will publish this in its entirety also on YouTube. We continue with mathematics syllabus for CSEC 2018. As of December 2025, this syllabus has not been revised, but there are plans to change the structure of the exam from 2028 and moving forward, with a few pilot projects now being conducted in a few Caribbean countries. The syllabus remains the same. The two main plan changes are: one, split the exam into two parts, and two, there will no longer be any alternative sections. All sections will be tested. Schedule of videos. These first three sections with 51 videos have all been published on YouTube in their entirety. Please make good use of them. Section 4, 5 videos published in their entirety out of 17. Section 5, statistics, 5 videos published on YouTube in their entirety out of 18. Section 6, 7 of those videos published in their entirety on YouTube out of 22. We are now at section 7. This is the 15th of 26 videos. And of course, after that, we will have to do geometry and trigonometry. And finally, section 9, vectors and matrices. And hopefully by April, May of this year, 2026, I should have that completed. Please note this disclaimer down here. This schedule is just a projection and it is not to be interpreted as a contract with anybody. I will quickly scroll through the rest of this introduction because you may have seen it before. Section 1, please make good use of all of those 33 videos especially, and many of them can even be used in the primary schools, grades 4, 5, and 6. Section 4, these that you see indicated in yellow have been published on YouTube in their entirety, the others only partially. If you need to get full access to these videos that are only partially published on YouTube, please see directions in the description below. Section 5, those published and the others partially. Section 6, those published and the others partially, especially from algebra. Please make very good use of these that are published, and even those that are partially published, especially since algebra seems to be a problem area for most learners. Section 7, relations, functions, and graphs. We have 26 videos here. Before we go on, just a reminder of the recommended textbooks that CSEC recommends, and out of those, the two that I would recommend would be those two. Disclaimer here, I get no financial or other benefits from the sale of these books. Also, we have a very good website with AI interactivity that deals with past CSEC math questions from paper 2. It is important that you learn, that you become familiar with how CSEC sets its questions for paper 2 and what will be considered good or correct answers to such questions. This is the URL for that website, which is shown here. That's the home page. There will be this link in the description below, so you can easily click on it and be redirected to this website. Also, a reminder that you will be provided with a formula sheet during the examination. And this formula sheet is included in the syllabus. If you have a full syllabus, you can have a look at it. If not, there is a link in the description below from where you can download this formula sheet. That's the top part of the formula sheet. So you don't have to memorize these formulae. This is the below part, but you do need to know when and how to use these formulae. So section 7, page 1, 5 objectives. We have completed all of those. Page 2, up to objective 9, we have completed all of those. Page 3, up to objective 13, we have completed all of those. And now we are here. We have completed objective 14. We are at objective 15. And then after that, we still have some more to do for this section. And some more up to 22. And furthermore, finally, up to objective 26. This section has 26 objectives. So you know where we are and where we need to reach for this section. Thus far, we have completed these 14 videos that you see up here. Those indicated in yellow have been published on YouTube in their entirety. The others are only partially published on YouTube. When I finish this one, objective 15, this one, it will be published partially on YouTube. So we are here, objective 15, and this is what it says. Use linear programming techniques to graphically solve, emphasis here is on that word, to solve problems involving two variables. And there are no explanatory notes here or examples and so on. So I will have to use my initiative and come up with some problems that we can look at. Let us revisit the last video where we ended, just to illustrate the principle of linear programming. That was objective 14. Draw a graph to represent a linear inequality in two variables. We ended that video by considering this one example as a preview of what we will be doing now. And that was example 7. And the question was, I think of two numbers, x and y. I double x and add 1 to that, and my answer is greater than y. If I multiply x by -2 and add 6 to that, my answer is less than y. By the use of a graph, show the region that will meet the requirements of x and y. And so we developed two inequalities for that. 2x plus 1 is greater than y. That's this first part here. 2x, double x plus 1, my answer is greater than y. That's this first one here. And the other one is -2x plus 6, and my answer is less than y. That is to say, multiply x by -2, that will give us -2x. We add 6, that's a plus 6. And my answer is less than y. That's this part here, less than y. So we get those two inequalities. Let's flip the two inequalities around to begin with y. And if we do that, then this greater than sign will become less than, and this less than sign will become greater than. So we get y is less than 2x plus 1. Well, if 2x plus 1 was greater than y, and you begin with y, then y is now less than 2x plus 1. And the other one, -2x plus 6 is less than y. If you flip that around, then y is now greater than -2x plus 6. So we have these two inequalities here. We will approach it in three parts. In part A, we will show the first inequality. In part B, we will show the second inequality on a graph. And finally, in part C, we will combine these two to show the region of all possible answers to the question. So these are our ordered pairs. if we take x as a domain, and then in this equation, that y would be the range. And for this equation, that y will be the range. Remember, we don't need all of those points. Since these are straight line graphs, we need at least 3. 4 will do fine. So we plot the graph and we get this. So yes, we know how to solve two simultaneous linear equations graphically, if these were equations. And the answer will of course be this one point down here, that one point there, which is 1.25 and 3.5. That is if we were dealing with simultaneous linear equations. Now we will modify this graph to show the inequalities and the region that will satisfy those equations. So this is the first equation. We plot the equation, we get this. But since it says less than, this red line, the solid red line, should actually be a broken line or a dashed line, because it says less than. And once we rectify that, then we will have to decide which side to shade, the upper left over on this side or the lower right over on this side of the line. So we corrected that matter of the line. Now, how do we decide which side to shade? We choose two test points. If we choose this point over here, which is -2, 5, and substitute it in this first inequality here, it says 5 is less than -3. That obviously is false. So we will not use that side over there. Let's try the next side. 2 and 1. When we substitute that in the inequality, we get 1 is less than 5. That is true. So we will shade this section to show the region that satisfies that inequality. So it will look like this. Y is less than 2x plus 1. Now let's consider the other inequality. We know it's an inequality, so we can begin now with the broken line, the dashed line, because that line is not included in the solution. Based on the inequality, we know this line is not a solid line because there is no or equal to. So it is a broken line. Now to decide which side to shade, lower left, which is this side down here, or upper right, that side up there. So we will use two test points, one on either side of the line. Let's use this one here, which is -3, 5. Substitute that in this inequality, and we get 5 is greater than 12. That is false. So we will not use this side. Let's see what the next side will give us. 2 and 10. You substitute the 10 for y and the 2 for x, and you come up with 10 is greater than 2. That is true. So yes, we will use this side as a region that will satisfy that inequality. So we get this. Y is greater than -2x plus 6. So okay, let's put those two together to see what we get. This is that one over here, and that is this one here. Note carefully the region that is common to both of them. This is the required region or area here, extending as far right as possible. Now this is the required region or area with many possible ordered pairs of x and y. Note that this region extends to the right indefinitely. So I think of two numbers, x and y. If I double x and add 1 to that, my answer is greater than y. If I multiply x by -2 and add 6 to that, my answer is less than y. So by the use of a graph, show the region that will meet the requirements for x and y. And as I said, this region here, going as far out as possible, will give us valid answers for x and y. So let's try one value. 4 for x and 5 for y. 4, 5. If we use these two inequalities up here, notice we get 5 is less than 9. That is true. And then we also notice that 5 is greater than -2. That is true. And then we do the same thing for the original two inequalities, and we find the answer is also true. Now, this is the basic principle of linear programming that we previewed in the last video. That is video 14 in this section. Very last thing we did. Now, I went through it in detail to make sure you understand what it is. Now, we will apply this in practical situations, and it gets a little more difficult. That example that we just did was not difficult. It was fairly simple. What follows may be somewhat more difficult than what CSEC requires, since there is no additional notes on this objective to say how much we need to do or how little we need to do. So just follow along as best as you can and try to understand the concepts involved. Even if you are not asked to draw the graphs, if they are given in the question, you do need to learn how to interpret such graphs. So what is linear programming? First of all, what it is not. It has nothing to do with computer programming and computer languages. Nothing. It's strictly mathematics. The glossary of your syllabus does not even mention it. This is that part of the syllabus. Notice all the L's here. Nothing about linear programming. You have linear expression. You have linear equation, but nothing about linear programming. So we have to look somewhere else. Linear programming, and you don't have to memorize these, but you have an idea what it is. Linear programming, LP, is a mathematical method to find the best outcome, like maximum profits at minimal cost, in a system described by linear relationships using an objective function, we will talk about that just now, what to optimize, and linear constraints, the limitations like resources and labor. It is a core tool of operations research, turning real-world problems like manufacturing, logistics, finance, and so on, into models to make optimal decisions. That is, finding the best solution. And where do you find the best solution? At the corners of the feasible region. We will be using that extensively, defined by the given constraints. So that is what we are doing. There are two main ways to solve linear programming problems. The first one is the simplex method, and you would think that because it names simplex, that it would be simple. Actually, it's fairly difficult, and you have to use matrices. So the other one is the graphical method, and this is best for problems with two variables, where you plot the constraints to find the feasible region and then consider its corners or vertices for the best possible outcome. Now, this objective requires only the second method. So this first method here, don't even think about it. This is the one we will be dealing with. Example 1. A manufacturer makes two types of products, P and Q. It requires 10 man hours and $6 in materials to make one product P, while it takes 8 man hours and $9 in material to make one of product Q. The manufacturer has a total of 1,200 man hours and $900 for raw material available for these two products. So the question is, show this information as a pair of inequalities, represent those inequalities from one above on a graph, and thirdly, how many of each type of product can be made. You understand that this one here is variable because it will be a region. So when we talk about objective function, the objective function is how many of each product to make for best profit. And when we talk about linear constraints, what are the limitations you have to make those objects? So show this information as a pair of inequalities. So here goes. If P is the number of product P and Q is the number of product Q, then for man hours available, 10P plus 8Q must be less than or equal to 1,200. And for money available, remember these cost $6 and $9 to produce. So 6P plus 9Q must be less than or equal to 900. So those are your constraints. We use that, get some ordered pairs. So choose some values for P, which would be the domain, and get some range for the other two based on the inequality we are using, and we plot the graph. And we get this. Looks familiar. Note one particular thing. These are the equalities. In these real-life situations, we will not use dashed or broken lines, as the point of intersection is also and especially considered. In other words, the points at the line are also very important. As a matter of fact, more important than other areas. So now we need to shade the area that is common to both inequalities. And that would be it. This area here is called the feasibility area. So your answer can fall anywhere in here. But you see, that's not what we are looking at. If we were doing this just for a math question, we could pick any answer in there and that would be fine. But we are looking at a business application. We want to know which answers in there or at the edges will be the best, meaning it costs less and you get the most profit. How many products of each type can be made? As I said, pick any point in here, any point, 20, 50, 40, 70, 80, 40, any point in there. Choose any point in the shaded area, including the lines. So if you choose this one here, you find that you use 800 out of your 1,200 man hours, and you use $670 out of your 900. But is that the best answer? Is that the best way to use resources to get the most possible profit? Let's try another number. Let's try this one here, which is 80P and 40Q. In this case, we are using almost all the man hours, and we are almost using all the money too. So that is fine. But it still may not be best, but it is better than the previous one we were looking at. So if we take some examples here, this is the table. If we choose 0P and 100Q, then we would have used up 800 of our 1,200 man hours. So that is true. And use up all $900. But will we get the most profit from that? And so on. We could go down like this. We will use this intersection point as well, which is here. That seems to be the ideal point. you're using up almost all your 1,200 hours and basically almost all your $900. But you notice we have fractions there. And that may be the ideal. Say 85 of P and 42 of Q. But that doesn't leave you any wiggle room or space for error or mishap, breakdown in machinery, and so on. What may be better is this one here. It is more reasonable. If a worker is ill, notice you use 1080 man hours as opposed to 1,200. So you have made space for that. And depending on the demand for the product and so on, you may find that this one here would be a better deal than this last one down here in red. So if you were working as a manager of that production site, depending on other factors as well, it may be best to choose 60 of product P and 60 of product Q. You have some leeway in terms of man hours, and you are using up your $900 full resources. So this answer here, notice that that answer is on that line. That may be the best answer. If you find this video useful and interesting, please like and share. That is to say, like and share. You may also consider subscribing to this channel. Example 2. And remember, we are looking at two variables. A printing company wants to buy two types of some new printers. Xerox, we will designate that as X, and Canon, designated as C. Each X costs $3,000 and it costs $40 per week to operate, to run. Each C costs $2,500 to buy and $60 per week to operate, paper and ink and so on. The company has $36,000 to purchase the new machines and wants to keep their weekly running costs to no more than $600. Show this information as a pair of inequalities. Represent those inequalities from one above as graph. And then there's a specific question. How many Canon machines can the company purchase if it needs at least 5 Xerox printers? So we have to do 3 things. Okay. Don't let that scare you. It is not as difficult as it looks. So this is our objective function, how many printers of each to buy. And this is our constraints, how much money we have to spend on maintenance and for purchase. So first of all, let's get the inequalities. If X is the number of Xerox machines and C is the number of Canon machines, then for purchase, 3,000 times X plus 2,500 times C must be less than or equal to 36,000. That's the amount of money you have to spend. And secondly, for weekly running costs, 40X plus 60C must be less than or equal to 600. So you have the two inequalities. And that may be the hardest thing about this question. So we have to show this information as a pair of inequalities. We can simplify these. So this can be simplified to that, and that can be simplified to this. So those are the two inequalities that we are now going to plot. We take some domain values for X and then see what we get for these other two. And we plot the graph, and this is what we get. Now, these that you see here are the equalities, but remember, we are keeping those lines as solid lines because we are using them. We need to shade the area that is common to both inequalities. which is that area you see there. And that area has a special name. It is called the feasibility area or feasibility region. So any answer in here will do if we are left to deal randomly with the number of Xerox and number of Canon printers. But we have a specific question. And the question says, how many Canon printers can the company purchase if it needs at least 5 Xerox printers? So we go to 5 Xerox printers, come up here, come across, and we come up with that answer. Of course, you can't get half of a printer because 7 will be there. You don't have enough money to buy 7 printers and to operate them. So the next best one here would be 6. So the company would be able to buy 5 Xerox printers and 6 Canon printers. That's one answer. So if you substitute that, notice 60 here is less than 72. So we are within our limit. And 28 here in terms of maintenance is less than 30. So we are well within our limits. Now, how many of each type of machine can a company purchase if it needs at least 5 Xerox? Now, they didn't say exactly 5. So what about if you decide to buy more than 5? You find a point to the right of 5x on the x-axis with a whole number for C in the top of the shaded area. So you could choose 7. Remember, it said at least 5. You could choose 7 and then come over here and see where you have a whole number, which would be here, and that point there will be 5. So 7x and 5c. And we could see that we are within our limit. 67 is less than 72, and 29 is less than 30. We are barely there. So we can do that too. It didn't say exactly 5 Xerox. It says at least 5. And we got an answer for 5. And now we have an answer for 7 Xerox. We could get 5 Canon printers as well. Now, next question. Can the company purchase 6 of each? This is much easier. So you come up here at 6. 6, you come up here at 6. And you come across here. And yes, we arrive at 6. So it appears from this graph, this company can purchase 6 Xerox printers. Remember, it said at least 5. Now we are saying 6 Xerox and 6 Canon as well. We do that and we find that we are within our limit in terms of spending and right there in terms of maintenance, paper and ink and so on. Can the company purchase 5 Xerox and 8 Canon? So you come up at 5 here and you go across at 8, and notice you are outside of that region. So obviously the answer is no, not 5 Xerox and 8 Canon printers. Now in terms of the cost, we are within our limit. But in terms of the maintenance, the expenditure to buy ink and paper and so on, that has shot up to 34, and we need to get to no more than 30. So in this case, the maintenance would be a problem, not the cost. Can this company purchase 4X and 12C? Obviously, now we are outside both cost and maintenance. Example 3. A farmer has 40 hectares to grow barley and corn and needs to decide how much of each to grow to maximize profits. The cost to grow and reap 1 hectare of barley is $60 and for corn is $40. The money available for this is $960. The total man days available is 72. Put in work throughout. Barley requires 1 man day per hectare, and corn requires 2 man days A man day is the work that a man could do in one day. So 2 man days. The profit on barley is $180 and on corn is $240 per hectare. I know it looks difficult and complex. Let's take them one step at a time. Find the number of hectares of barley and corn that the farmer should plant to get the most profit. So this is our objective function to get the most profit. And our limitations or linear constraints are how much money is available and, of course, how much land is available. That will be the profit. These two here will not come into play, but we just write them down. So it looks like we have 5 constraints. Well, it looks like we have 6. 1, 2, 3, 4, 5, 6. Let's plot them on a graph. We get some points. And we plot them, and this is what we get. Now remember, we are still dealing with 2 variables, even though we have 3 lines on that graph. The 2 variables are how much barley and how much corn. Let us say that you were not asked to draw this graph. You were given a graph and then asked some questions after it. That, I think, would be reasonable for CSEC, rather than to ask you to draw a graph like that in an exam. So these are the equalities. We now need to share the area that is common to all 3 inequalities, which would be this area here, that area there. And that area is called the feasibility area. In other words, anywhere in there will work. But this is not just anywhere in there. This is which is the best point to give the most profit. And generally, you will consider the 5 corners of the feasibility area, the 5 corners. That is this one here, that one there, that one there, this one here, and this one here. If we consider this one, which is 0, 0, we can ignore that. You're not going to plant 0 hectares of corn and 0 hectare of barley. Ignore that. We can consider this one down here, 16 barley and no corn. And if we do that, remember $180 profit there, $240 profit there, you will get a profit of $2,880. Or we can consider this point up here, where we now have 0 barley and 18 corn. If we calculate that, we get a profit of $4,320. That's for those 3, which generally will not be your answer. Your answer will be one of the other 2 points. So let's consider this one here, 4 barley and 16 corn. We calculate the profit and we get 4,560. Remember, 180 for barley and 240 for corn. So if we take 4 barley and 16 corn, this is the profit we will get. And then let's consider the other one, 8 barley and 12 corn. And now we get $4,320. So that is even less than the last one we were looking at. So our answer will be 4 hectares barley and 16 hectares corn. That is our best option. This one here. And notice it is actually where those 2 lines intersect, the lines themselves. That is why I said we keep solid lines, because the lines themselves are used. As a matter of fact, it is at the lines, at the corners, at the edges, at the vertices that we will find our best answer. You could choose any other point in here and you will not get as good an answer as that. So that is what the farmer should plant, all other things being equal. Example 4. For a camp of up to 120 children, 2 types of tents are available for hire. The larger tent sleeps 8 and costs $30 per week. The smaller tent sleeps 5 and costs $14 per week. The total number of tents must not exceed 20. Total funding for rental of tents is no more than $420 per week. Find the number of each type of tent that the camp can get at the funding available, and the condition that it must not be more than 20. So we have two variables, large tent and smaller tents. So this is our objective function. And here we have our linear constraints. What limitations are there? So we plot some points, large, small, for that, and then this equation and this equation, and we get those points, those ordered pairs. For example, if you take 4 of that, we could get 17.6 of that for that equation, and so on. So we plot the points, draw the graph, and this is what we get. Find the number of each type of tent that the camp can get for the least amount of money within the available funds. So we need to shade the area that is common to all three, which is this. Now remember, any value in here will not work because you may not be able to accommodate the children. So this is the feasibility area. So 0, 0 has no meaning. So let's ignore that. This situation here, which is here, if we rent 20 small tents and 0 large tent, then we will only be able to accommodate 100 campers, and we need to accommodate at least 120. So that will not work right there. In terms of the money, we are within our limits, 14 times 20, which is 280, which is less than 420. So we are within our budget limit. And in terms of number of tents, we have 20 small tents. So the budget here will work, number of tents will work, but the number of people to accommodate will not work. 20 small tents will only take 100 campers. We need space for at least 120. So that will not work. Let's take this other point down here. This time, we are dealing with 14 large tents and 0 small tents. If you take 14 large tents, that will take 8 persons each. You are going to accommodate 112 persons, not 120. In terms of money, you just barely spend your money that you have, 420 and 420. And in terms of tent, you have 14 and you are allowed 20. So we still have a problem here. So those 3 obviously will not work. Let's put them on the table. None of these will work for obvious reasons. So now let's try this point here, 7L and 30S. If we do that, we can accommodate 121. We have 120. So that is fine. We have spent $392 and we have 420. And 7 plus 13 is 20. So we have the 20 tents. So all of those seem to be in place. 7 large tents, 13 smaller tents. That will accommodate 121 children. We need to accommodate 120, so we have 1 extra space. Our budget, money spent, $392. We had 420, so that's fine. We are allowed up to 20 tents, and we have just that amount. So this here seems to be fine. Let's look at the other one down here, 11L and 6S. If you do the calculation, we don't have enough space. That's 118. We need space for 120. The finances, 414 you spent, and you have 420 fine. Amount of tenths, 11 plus 6 would be 17. You are allowed up to 20 tenths. So this is okay. That is okay. We don't have enough space for the 120 campers. Even if you say you put one each in 2 of the larger tents, maybe certain regulations and stipulations may not allow that. So if you put that down here, we don't have enough space. 118, and we want to accommodate 120. This 414 is fine. You had 420, just within there. 17 tenths out of 20, that's fine. So we have a problem here. So what does that leave us with? D or E? I wouldn't take a chance with E, so I will choose D. 7 large tenths and 13 smaller tenths will accommodate 121 campers. I should have no more than 120. I'm spending $392 out of the 420, and I do have 20 tenths, but that is what I am allowed. And last example, we will do example 5. Before we do that, let's consolidate what we have learned so far. Linear programming is a mathematical technique used mainly in business to maximize profits and minimize costs. It can be done using matrices, which is not required by this objective, or by the use of graph, which is required by this objective. In using graphs, there are a sequence of steps to follow. You don't have to learn all of these. I am going to go through them very quickly. Define variables, establish constraints, construct objective function, graph the constraints, establish feasibility region. Normally, they would say add ISO profit line. We are not doing that. Instead, we look at the corners of the feasible region, and then we choose the optimal solution. Example 5, company PQR produces 2 models of fans, regular R and super S. Monthly machine capacity is 400 hours for both. R requires 1.5 hours of machine time, while S requires 5 hours. Environmental regulations limit production of both to 150 units per month. Each R costs $80 to produce and is sold at $105, while each S costs $164 to produce and is sold at $199 each. The total expense for R and S should not exceed $14,500. Use graphical linear programming to determine what numbers of R and S will give the most profit. So we have to define our variables, and those are the numbers of R and S per month. So you can say let the number of R's be R and let the number of S be S. You can do that, or you could let them be represented by X or Y, but it is actually easier to use just the R and S, which is what we will use. Having done that, we will establish the constraints. What are the limitations? First of all, machine hours, 1.5 for 1 R and 5 for 1 S, and total hours must not exceed 400, as we have up here. Secondly, total cost, $80 to produce 1 R and $164 to produce 1 S, and that should not exceed $14,500 as we have here. Thirdly, number of units. R plus S must not exceed 150 units per month. And we have these other two. R must be greater than or equal to 0, and S must be greater than or equal to 0. Now we have to construct our objective function. This is the one that has to do with profit. Construct objective function. So the profit will be 105 minus 80 times R plus 199 minus 164 times S, which works out to be $25 per unit of R and $35 per unit of S. So the profit is 25 R plus 35 S. That is extremely crucial. Profit 25 R plus 35 S. Now we have to graph the 5 constraints. Well, these two are fairly easy. These 3 are what we have to concern ourselves with right now. We need to find the ordered pairs to plot the graph. We will use S as the domain, the x-axis, using random numbers from 0 to 150. Remember, that's the number of units that could be produced, 150 total. And then we will calculate the corresponding R in each of the 3 equations or equality. So those are our 3 equations. If we choose 4, for example, as S, we will get that for R according to this equation here, this for R according to that equation there, and that for R according to this equation here, and so on. We will plot those points, and we get this. Not forgetting R is equal to 0 down here, and S is equal to 0 over here. So those are our 5 constraints. Now, where is the feasible region? This area here, in here. So we will shade that feasible region. So we establish this feasible region. Next, we will have to determine where we will have the best or the most profit. We will skip the ISO profit line and instead consider the corners of the feasibility area. It's a little harder to use the ISO profit line. So we will use the easier method, the corners of the feasibility area. We have 5 corners. And as we will apply this profit equation to each corner. First corner here is 0S and 0R. That doesn't make sense, so we will ignore that. Then we have this one here, 0S and 150R. This one here, 30S and 120R. This one here, 66S and 50R. And this one down here, 80S and 0R. Let's consider each one using this profit equation here. At 0S and 150R, this is the amount of profit the company can make. And at 66S and 50R, that is the amount of money the company can make. So we will have to evaluate these. Now, right now you are thinking there's not much evaluation to do because you could see that you have the most profit here. So determine optimal solution. As I said, we'll briefly consider that just now. These are our options for the 5 points. And as you can see, this one here, 30S and 120R will give the most profit. So the best option in terms of profit is this, which is 30S and 120R. That should be more than enough for this objective. Objective 15, use linear programming techniques to graphically solve problems involving two variables. That brings us to the end of video 15, Objective 15, Section 7.